Very well, we will continue our discussion. What we did in the previous class was to begin with the equation of motion, play with it and discover various conservation laws. And one of the quantities that is conserved that we ran into is this Laplace-Runge-Lenz vector, and what we will do now is use this to get the equation to the orbit. Now this is again, there is a novelty in this process, because whenever you solve an equation of motion, means the purpose of the goal of a problem in classical mechanics is to find what is it that characterizes the mechanical state of a system and how does the system evolve with time. Now when you solve this problem, you get the trajectory of the particle or of the system in the phase space or in the configuration space, or you get the trajectory, you get the orbit, means a closed trajectory is an orbit, but essentially you are looking for the solution, you are looking for the trajectory, right. You have to find, the problem of mechanics is to find this trajectory, and the method to get this trajectory is by solving differential equations, either the Newton's equation or the Lagrange equation or the Hamilton's equation. What we will do is to just play with this Laplace-Runge-Lenz vector. We will not solve the differential equation, we will not solve the equation of motion and still get the trajectory. Now is not that fun? Now let us see how we do that. So we will get it by simply taking the scalar product of the Laplace-Runge-Lenz vector with the position vector, that is all you do, and by just taking this scalar product we will get the orbit equation, okay, which is a completely different process than solving the differential equation to get a trajectory. So let us take the dot product with the vector r, and you have two terms. R of course is the radial vector, so the dot product of kappa times E rho with r gives you kappa r, and on the right hand side you have got the dot product of the Laplace-Runge-Lenz vector A with the position vector. Now let us reverse the signs in this equation. So instead of V cross H, I have H cross V in the first term, okay. Instead of this minus sign I have got a plus sign over here, and on the right hand side I get a minus sign over here. So I just do a sign reversal, and now I have got a triple product, and I can always interchange the cross and the dot. So let us do that. So it is H dot V cross R plus kappa r, okay, but we have met this quantity earlier, V cross R. It is the negative of the specific angular momentum, right. R cross V is the specific angular momentum, V cross R is the negative of the specific angular momentum, it is right. So we now have the dot product of H with the negative of H, so that gives us minus H square. Then you have kappa r, and this is equal to minus A dot r, which is A r cosine phi, where phi is the angle between the Laplace-Runge-Lenz vector and the position vector. Now if you look at this equation, this already gives us the orbit equation, because it tells you the relationship between r and phi, okay, which is what an orbit equation is, and some of you will recognize what this equation is, but we will rewrite this in a form which is more familiar to us. So we will just carry out some transformations. So I take r common between this term and this term and bring h square to the other side of the equation. So, it is r times kappa plus a cos phi equal to h square, which essentially means that r is equal to p over 1 plus epsilon cosine phi, which is an equation to the ellipse, right. This is in a very familiar form. In polar coordinates, the equation to the ellipse is essentially p over 1 plus epsilon cos phi, right, epsilon being the eccentricity. So this equation and this equation is no different, it is just a rearrangement of that equation, right, and we got it simply by constructing the scalar product of the Laplace Runge-Lenz vector with the position vector. We did not solve any differential equation, we did not integrate the equation of motion, and we get the trajectory. That is wonderful, is it not? So, here we go, this is the equation to the ellipse, and this is the kind of geometry we are working with. We need to find what this eccentricity is, and this eccentricity E or epsilon is coming as a ratio of the magnitude of the Laplace Runge-Lenz vector with kappa, but this is in our own units, mind you, and in some other units some of the constants will get cancelled when you take this ratio. So, we need to get that eccentricity, and to do that what we do is to take the scalar product of the Laplace Runge-Lenz vector with itself. So, we take the scalar product of the left hand side with itself and the scalar product of the right hand side with itself. So, a dot a will give us a square on the right hand side, and on the left hand side we have got v cross h, which is nothing but hv times the unit vector, because h is obviously orthogonal to v, right. The angle between h and v will have to be 90 degrees because h is defined as r cross v. So, it has to be orthogonal to v. So, there is no angle between h and v other than 90 degrees, it is always pi by 2. So, this dot product of v cross h with itself will give us the square of hv. The dot product of this quantity with itself will give us kappa square. This is just the unit vector dotted with itself, which will give you the number 1. So, the dot product of this quantity with itself gives us kappa square, and then you have got the cross terms between these, and since the scalar product is commutative, you get a factor of 2 over here, okay. Or you should have a minus sign, but I have written it with a plus sign because instead of v cross h I have written an h cross v over here. So, that will not be a worry, okay. So, this is the result that we get, and we now have this h cross v sticking over here. We expand this because h itself is the specific angular momentum r cross v, and we will carry out this expansion. So, this is the dot product of this outer vector with v times the middle vector v minus the cross product, the dot product of this vector v with the adjacent vector v, which gives us v square times the remote vector, which is r. So, this is again the back-cab rule which I have used. So, we have got this h cross v, and now what we need over here is h cross v dot r. So, h cross v we got, now we dot it out, we take its scalar product with the position vector r. So, we take the scalar product of this right hand side with the position vector r. So, you already have a v dot r, and from the projection of v on r we get another v dot r over here, and from the second term we have minus v square, and then the dot product or the scalar product of this position vector with r. So, this is minus v square r dot r, and if the angle between v and r is xi, then v dot r is Vr cosine xi. So, you get the square of this because there are 2 of these terms. So, it is Vr cosine xi square, and you have got a v square r square over here. So, you can take the v square r square as common and recognize that 1 minus cos square theta is sin square theta. So, you get the minus sign common and the result is v square r square sin square xi. Okay. So, this is what we get for this term over here. So, let us simplify this, and this equation which has got hv square in the first term. In the second term you have 2 kappa over r, there is a plus sign, but this box h cross v dot r has got a minus sign over here. So, the result is minus 2 kappa over r, which is this coefficient here, and then the v square r square sin square xi, and this kappa square comes here, and then you have got the a square on the right hand side. So, there is no new analysis, it is just a rearrangement of terms. Now, this is a very nice form, because you can recognize this v r sin xi to be the magnitude of the specific angular momentum, because that is r cross v, right. So, I take h cross square h square as common in the first two terms. It is already sitting there explicitly in the first term, and since I have taken it as common, I must divide the second term by h square. The third term I leave alone as kappa square, and then I can cancel this denominator h square with this v square r square sin square xi, because h is r cross v. So, it is r v sin xi, that is the magnitude of h, and the square of it in the numerator cancels the square of it in the denominator. So, now you have a rather simpler form, okay, in which the sign of the angle disappears, the sin xi disappears. Okay. V square minus twice kappa r is twice the energy. Okay. This is in units of mass, right, because this is the specific mechanical energy. mv square by 2 is what we will interpret as the kinetic energy, right. This is v square. So, it is twice the kinetic energy, and this is twice the potential energy, twice the specific kinetic energy plus twice the specific potential energy, because that is how we have defined the kappa as well. So, this is nothing but twice the energy. So, h squared twice energy or specific mechanical energy plus kappa square equal to a square, and a rearrangement of these terms in which you divide this entire equation by kappa square gives us a over kappa, and we needed the a over kappa to get the eccentricity, if you remember. Okay, we got the equation to the ellipse in which we had the eccentricity, but the eccentricity was in terms of a over kappa, and we have it now in terms of known quantities which are the energy and the angular momentum. So, a over kappa is this quantity, it is the square root of the left hand side. So, it is the square root of 2 e h square over kappa square plus 1, and this is now the complete orbit equation in polar coordinates. So, this is the equation to the ellipse, and we have achieved a lot just by playing with the equation of motion. We discovered various conserved quantities, we connected these conserved quantities with symmetries, and these are obviously extremely important relations in rocket technology, in satellite trajectories and so on, because depending on the eccentricity you get different kinds of orbits. So, you may have an open trajectory, you may have in a hyperbola if the eccentricity is greater than 1, you may have a parabola if the eccentricity is exactly equal to 1, and then you may have closed orbits, which is what will happen if the eccentricity is less than 1, and then if the ellipse is degenerate, the major axis and the minor axis, if they are equal, you get a circle. So, that is what will happen if the eccentricity is 0, and these are of course very important in rocket technology and satellite shaping, orbit shaping and so on. So, you have to really maneuver these eccentricities if you have a deep space probe, for example, you will need to launch the object and let it go outside the Earth's gravitational pull in closed orbits. You might have to send it in a hyperbolic orbit. So, you will, this is what is called as orbit shaping, and one really has to adjust these parameters to get whatever desired trajectories you have. And here you can see that these eccentricities can be easily adjusted by changing the ratio of the major axis to the minor axis, or vice versa, the minor axis to the major axis. Now, these are the essential parameters. Now, this distance, which is the minimum distance, let us deal with ellipses, because these are the closed orbits that we have to work with for satellite trajectories or for orbits of planets in the solar system. The closest approach is what is called as the perigee. This is the point of perigee. The minimum distance will be given by this term when the denominator is the largest, which is what will happen when the cosine is the largest, which is what will happen when the angle is 0, because for phi equal to 0, cosine phi becomes +1, which is its largest value that it can take. So, the minimum distance, the distance to the perigee, is p over 1 plus epsilon. The apogee is the maximum distance, which is p over 1 minus epsilon, and you can see that if you just add these distances r and r prime from the two foci, then this 2a is a constant, and you can get it by simply adding the minimum distance and the maximum distance. And this allows us to write the numerator p in terms of the eccentricity and half the major axis. So, this is a familiar form in which you write the orbit equation. And for a degenerate ellipse, eccentricity is 0. So, this will be minus kappa over 2a. Now, these are just rewriting these relations in known forms or in more familiar forms, and of course, these are important for various technology applications. Means you have, most of you are, I do not know if you are listening to my lecture or under the desk using your cell phone to send an SMS joke to your friends, and these cell phones require GPS system, okay, and all of these GPS systems are monitored by various satellites, and at any given time there have to be a certain minimum number of satellites which are visible from a point in space, and you can see that all of these orbit equations and all the properties which govern the orbit equations, the conserved quantities and how these are to be changed by firing rockets if you want to do some orbit shaping, that these are essential elements of modern technology. Now, what I will be doing is to use the polar coordinate systems, and we have discussed this in unit 3. So, I will not spend any time developing the polar coordinate system, I will use it. I will just remind you that in the polar coordinate systems, actually we could do with the plane polar coordinate system, but we also have to deal with the angular momentum which is perpendicular to the plane of the orbit. So, if you want, you can think of this cylindrical polar coordinate system. Motion, of course, is confined to a plane because angular momentum is conserved, and this is the specific angular momentum rho square phi dot. The angular momentum itself is in the direction Ez, which is perpendicular to the plane of the orbit, and in this coordinate system we will work with the Laplace Runge-Lenz vector, which is v cross h minus kappa times E rho being the polar unit vector along the radius in the plane. Now, let us have a look at the direction of the Laplace Runge-Lenz vector. So, this direction is of course given by v cross h minus kappa e rho. So, this is the direction of e rho, this is the direction of the velocity of this planet going around the sun. Okay. The angular momentum is out of the plane of this figure toward us, the manner in which this ellipse is going, right, the manner in which this planet is going in this plane. So, this is the direction of the angular momentum, which is seen by an arrow which is perpendicular to the plane of the screen pointed toward us. So, that is the direction of angular momentum, and you can therefore determine the direction of v cross h. Okay. So, you need the direction of v cross h, and from this v cross h you must subtract kappa e rho to get the Laplace Runge-Lenz vector A. So, now we have got we have got v cross h. From this you must subtract kappa times e rho. E rho is from the sun to the planet in the direction of the position vector. So, this is the direction of e rho, this black arrow over here, minus e rho will have a direction opposite to it, but parallel to it and scaled by the factor kappa. So, minus kappa e rho will be anti-parallel to e rho, right. So, this is minus kappa e rho, and if you take v cross h minus kappa e rho, you have to take this vector v cross h minus kappa e rho. So, the Laplace Runge-Lenz vector will be this red vector. Okay. This is the direction of the Laplace Runge-Lenz vector. Now, let us have a look at the time derivative. We already know it is a conserved quantity, so its time derivative must vanish, but let us confirm that its time derivative actually vanishes, because we had not done that. We got the conserved quantity by playing with the equation of motion. Okay. Now, we reassure ourselves that its time derivative vanishes. So, let us take the time derivative of the Laplace Runge-Lenz vector. Okay. So, the time derivative of the Laplace Runge-Lenz vector will be dv by dt cross h plus v cross dh by dt from the time derivative of this term. Kappa is a constant, and then you have the time derivative of the unit vector, and these unit vectors of course change from point to point and from time to time. Now, the time derivative of the angular momentum of course vanishes, because angular momentum is conserved in the central field. So, dh by dt will go to 0, and now you are left with these two terms, dv by dt cross h minus kappa times d by dt of e rho. But this we know from our knowledge of the plane polar coordinate systems. We had done this in unit 3, that the time derivative of the unit vector e rho is equal to phi dot times e phi. The change in any unit vector is always orthogonal to that. So, the change in unit vector e rho will be along e phi, and its magnitude is something that we determined explicitly in the previous unit, unit 3, and we found that d e rho by dt is equal to e phi times phi dot, and this is the term which will go here. Okay. So, d e rho by dt will be replaced by phi dot times e phi. So, let us do that. So, we have dA by dt, which is the rate of change of the Laplace Runge-Lenz vector, equal to dv by dt cross h minus kappa times this quantity here, which is phi dot e phi. Okay. That is the relation that we have on the screen. dA by dt is dv by dt cross h minus kappa phi dot e phi. Fair enough. Now, what do we need? We need dv by dt, that is acceleration. Okay. And acceleration is the force per unit mass. So, it is a specific force, and we are developing this entire analysis for these quantities which are qualified by the term specific. We dealt with the specific mechanical energy, we dealt with the specific angular momentum, and now we deal with the specific force, which is a force per unit mass, which is acceleration. Okay. because F is equal to ma. So, per unit mass it is dV by dt. So, what we now need is dV by dt, or in other words we need the force and we need the interaction. What is this interaction? This interaction must be plugged in to find what dA by dt is. Unless we know the interaction, we cannot proceed. Okay? We must write the explicit value for dV by dt. We need the force. Now, this force, we know this is the potential energy minus kappa over r, right, and the force is the negative gradient of the potential. So, we know that this force is minus kappa over rho square, okay, it is the negative gradient of the potential. So, we put dV by dt equal to minus kappa over rho square times E rho. So, instead of this quantity dV by dt, we have this minus kappa over rho square E rho, and now everything is written in terms of these polar quantities rho and phi and the constant kappa. Okay. And you already know that in the cylindrical polar coordinate system, E rho, E phi, E z constitute a right handed triad of unit vectors. So, the cross product of E rho and E z is equal to minus E phi. So, minus E rho cross E z, which is what you have over here, minus E rho, this minus sign, minus E rho cross E z is equal to E phi itself, and you find that the first term is exactly equal to the second term. You have got a phi kappa phi dot scaling the unit vector, and the first term and the second vector are exactly equal, they cancel each other, and the time derivative of the Laplace-Runge-Lenz vector vanishes. So, we have reassured ourselves that the Laplace-Runge-Lenz vector is a constant. Okay? Not surprisingly, because we in fact got it as a conserved quantity. But now, in ensuring that it is a conserved quantity, we did make use of the fact that the force is 1 over r square. Okay? This 1 over r square has been used in assuring that the Laplace-Runge-Lenz vector is a constant. If we had not used this, we would not have been able to convince ourselves that A is a constant of motion. So, now if you have this ellipse and there is a certain quantity which is conserved, okay, and we already saw that this conserved quantity A in the previous figure, you saw that it was from the focus to the perigee, and the constancy of this vector is what really prevents this ellipse from precessing. That if you have an ellipse like this, the reason it does not precess and go over to another orbit, okay, the conservation of energy or conservation of angular momentum does not guarantee that the ellipse will not precess. What guarantees is that this direction from the focus to the perigee is fixed, and if that direction is fixed, the ellipse itself is fixed. Okay. So, this is the reason there is no Rosette motion, because if you look at this precision from a distance, if you go far enough, it would look like the petals of a lovely rose, but the motion is still beautiful even if it is not Rosette. So, in this Rosette motion, the angular momentum is conserved, the energy is conserved, but the orbit is not fixed. So, the fact that the two bodies Kepler problem, and it is the same thing with the Bohr problem in quantum mechanics. If you look at the hydrogen atom, you have an electron which is going around the proton, and the potential is 1 over r, the force is 1 over r square, it is the Coulomb force in this case, and it is a great wonder of nature that gravitational force and the Coulomb force, both are 1 over r square forces. Now, this potential and for the associated orbit, we can find that the orbit remains fixed, and the fact that the force is 1 over r square was an integral factor in proving in our previous slide, as you see here, that this dV by dt, the force equal to 1 over r square force, is an essential part of the proof that the Laplace-Runge-Lenz vector is a constant, because if this were not so, the first term would not have cancelled the second term to give a 0, right. These two terms, the first term and the second term, they had to kill each other exactly. Only then would the Laplace-Runge-Lenz vector be a constant. So, we needed to know the force, and let us have a look at the geometry once again. You can immediately see that the Laplace-Runge-Lenz vector must be orthogonal to the angular momentum, okay, because if you take the dot product of the Laplace-Runge-Lenz vector with h, the first term is a triple product with h appearing twice, so it would vanish, and the angular momentum is of course orthogonal to the position vector. So, this scalar product goes to 0. So, that tells us that the Laplace-Runge-Lenz vector is in the plane of the orbit, but in which direction is it? It is in this plane, but you can draw a number of vectors in this plane. So, let us draw it. We having known that it is in the plane of the orbit, let us find what its direction will be, and let us do it for just one point. Let us do it for, let us determine it at the perigee. Now, this is the perigee, okay. What is the direction of V cross H at this point? V is from bottom to the top, H is from the plane of the paper toward you. So, what is the direction of V cross H? So, V cross H minus kappa E rho. E rho is from the focus to the perigee, minus E rho is like this, right. So, you can find that the direction of the Laplace-Runge-Lenz vector is from the focus to the perigee, and what is going to happen is that if this is the direction of the Laplace-Runge-Lenz vector for the point at the perigee, it will have to be the same no matter where the planet is, right, because it is a constant. It is a constant of motion, it is a conserved quantity. So, throughout the orbit, wherever the planet is, the direction of the Laplace-Runge-Lenz vector will always be this, and we now know that if the direction is always from the focus to the perigee, then the direction of the major axis itself becomes fixed, and the ellipse gets fixed, and the ellipse cannot precess, okay. So, there will be no Rosette motion. The fact that there is no Rosette motion is because of the conserved quantity, that the Laplace-Runge-Lenz vector is a constant of motion, it is a conserved quantity. And now, we ask the question that we know what fixes the orbit, it is the constancy of the Laplace-Runge-Lenz vector, but we have used the fact that the force is 1 over r square. Now, we know 1 over r square is the force between two masses, but we know it because Newton told us, okay, because you and I did not discover the law of gravitation. I certainly did not, I do not know about you, okay. Newton, we got it from Newton, and in fact the first person to know about it was Halley, after whom Halley's comet is famous, and this is very interesting because we discussed earlier how Kepler deduced that the orbits are ellipses. So, Kepler said that the orbits are ellipses because he did curve fitting to Tycho Brahe's experimental data. And then Halley later asked this question to Newton, that what would be the orbits, what will be the equation to the orbit, what will be the trajectory like, and Newton said it would be an ellipse, but Newton's basis was different. He did not say it on the basis of Kepler's laws nor on the basis of Tycho Brahe's data, but because Newton had invented calculus at his age of 22, 23 thereabout. There was no idea of function, limit, etc. So, he invented calculus, he set up the differential equations, he deduced, he discovered the law of gravity. So, he was able to plug in that force in F equal to ma and then integrate it to get the ellipse. It was a totally different ball game, okay, amazing. And now we again invert the question, that given the constancy related to conservation of Laplace-Runge-Lenz vector, could you have discovered the law of gravity? You know that the law of gravity is essential to the demonstration of the fact that the Laplace-Runge-Lenz vector is a constant, right. 1 over r square was essential. Now, if you did not know that 1 over r square is the nature of gravitational force, could you have discovered it if you had known that the Laplace-Runge-Lenz vector is constant, okay. So, this is the moral of the story, that you can invert these questions and discover the laws of nature by looking at these constant quantities. So, you have got a conservation principle, and from this conservation principle you can deduce what the law of nature is. But there is one question that remains to be answered, that what is the nature of this symmetry? We have got a conserved quantity which is the Laplace-Runge-Lenz vector, and what is the symmetry associated with this? Okay. When we encountered the conservation of energy, we discovered the symmetry, which is symmetry with respect to changes in time, evolution with respect to time. When we met the conservation of angular momentum, we connected with the symmetry with respect to rotations, right. And as I pointed out, I want to repeat this point, that Eugene Wigner elucidated to us that it is now natural for us to try to derive laws of nature and to test their validity by means of the laws of invariance, rather than derive the laws of invariance from what we believe to be the laws of nature. So, this is invert thinking which can lead us to new physics. We can discover new laws of physics using this technique. So, the symmetry associated with the constancy of the Laplace-Runge-Lenz vector is the fact that the force must be 1 over r square, that the potential must be 1 over r. It is not a geometrical symmetry, right. It is not like something like rotation, it is not changes, it is not like translational symmetry, like taking an object from here to here in homogeneous space, or it is not like taking an object and rotating it in isotropic space in which the properties of space are the same in all directions. So, this is the different kind of symmetry. You can call it as accidental symmetry if you like, and in fact this was in fact called as accidental symmetry, but a more appropriate term for this is dynamical symmetry. The reason it is called as dynamical symmetry, because it comes from dynamics, it comes from the cause effect relationships, it comes from the nature of the interaction. The nature of the interaction between these two masses is given by the 1 over r potential Gm1 m2 by r, the force is given by the corresponding 1 over r square law, right. it is this dynamics, it is this nature of the physical interaction which goes into the heart of the constancy of the Laplace-Runge-Lenz vector. This is connected with the conservation principle, and this conservation principle has a corresponding symmetry as one would expect from Noether's theorem, and this symmetry is therefore called as dynamical symmetry, and this is known as the Laplace-Runge-Lenz vector. Lenz name is also associated with this. This is not the same Lenz who we meet in the Faraday-Lenz law. This is the Lenz, Wilhelm Lenz, who dealt with the quantum mechanics of the hydrogen atom, where you also have the 1/r potential, and there is a similar feature in which was studied by Wilhelm Lenz. And we basically conclude this topic over here, but I will suggest a little bit of further reading, because the ideas have very deep and profound consequences in physics, because symmetry and conservation principles, they govern fundamental laws in physics, these connections. The implications are used to test the standard model of physics, to explore if there is physics beyond the standard model. I will strongly encourage you to listen to Feynman's lecture. It is available on the web. You do not have to write down this link. If you just Google Feynman lectures online or Feynman's messenger lectures online, or this TUVA project, or there are many other links, and Feynman has got a wonderful lecture on this topic. So I will strongly encourage you to read it, to listen to that lecture. There are other symmetries in physics which are important. You have continuous symmetries, the translations and the rotations that we have already discussed. Then there are these dynamical symmetries that we have discussed. The dynamical symmetry is the Laplace-Runge-Lenz vector in the context of the quantum mechanics of the hydrogen atom. It is known as the Fock symmetry or the SO4 symmetry. Then there are discrete symmetries like parity, charge conjugation, and time reversal. Okay, and there is a very famous Lorentz symmetry which is connected with the PCD theorem through the this was known as the PCD theorems proved by Pauli, and there is no experiment in physics that has ever been done in which the PCD symmetry has been violated. So this becomes a prediction of the standard model of the particle physics. Any departure from this will be a test on the standard model, and it will be a suggestion of whether or not there is any physics beyond the standard model. These are some of the issues which people are working with, and these are the essential elements of the standard model of physics, that there are a certain number of elementary particles, what are the forces, okay, what are the known forces at least, and this standard model requires the Higgs boson for its completion, which is one of the main objectives of the experiment at the Large Hadron Collider. And these are some very exciting issues which come out of these considerations: symmetries, conservation laws, discrete symmetries, Lorentz symmetry, and if there is any physics beyond it, and so on, right. In fact, quite recently, just the year before last, the Nobel Prize went for the spontaneous breakdown of symmetry, and there is another kind of symmetry that you normally expect, which is the symmetry between matter and antimatter, and if this symmetry is seen to be broken, then what are the reasons for it and how does one understand it. And the Nobel Prize for 2008 went to Nambu, Kobayashi, and Maskawa for throwing some light on these issues. These are clearly beyond the scope of these of this course, but these are some suggestions for further reading for some of you, and they all come from this basic idea that we have discussed, which we can understand even in terms of simple two-body Kepler problem. Okay, that for every symmetry principle there is a conservation law, and for every conservation law there is an underlying symmetry, and this whole thinking of going to the physical law from the symmetry principles is something that we began with Einstein. We will keep showing you this picture of Einstein smoking, but we will keep reminding you not to smoke, I think if at the end of this course, if I can discourage smoking, it will be an achievement enough, I would say. That is the real message. I will like to conclude by quoting from Einstein's tribute to Noether, who very sadly died rather young, and Einstein wrote in the obituary which was published in New York Times in 1935, and what Einstein says about Noether is that in the judgment of most competent living mathematicians, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. In the realm of algebra, she discovered methods which have proved to be of enormous importance. Her unselfish, significant work over a period of many years was rewarded by the new rulers of Germany with a dismissal, which cost her the means of maintaining her simple life and the opportunity to carry on her mathematical studies. So she went through a lot of injustice in Germany at her time. But with that, I conclude this particular unit. If there are any questions, I will be happy to take. In the next unit, we will discuss inertial and non-inertial reference frames. We will try to understand causality, and if there are, what is it that is behind the principle of causality, what kind of effects do these generate, and do all effects that we see come from known causes, or they are results of causes which do not exist, which is a fictitious cause, but that is for unit 5. So that is what we will discuss in the next unit. If there are any questions, I will be happy to take.
Classes we have discussed the merit of Lagrangian mechanics.
Yes.
As it is easy to identify the conserved quantities. So even in the Newtonian regime also, I think now it is easy to recognize conserved quantities.
Well, so far as the underlying physics is concerned, it is not different in Newtonian mechanics or Lagrangian mechanics. The foundations of the two schemes are completely different. The foundation of Newtonian mechanics is in the principle of causality, that there is a cause effect relationship, that a stimulus which is a physical interaction generates a response, and the response is linearly proportional to the force, to the stimulus. Okay? F equal to ma, that is the heart of Newtonian mechanics. So this stimulus response connection, the linear response of a system to a stimulus, is the basis of Newtonian formulation. Okay? The cause effect relationship is not invoked at all in the Lagrangian or the Hamiltonian formulation. The Lagrangian formulation and the Hamiltonian formulation makes no reference to the cause, it does not talk about the effects, it only talks about how a system evolves as a function of time, which is the main goal of solving a mechanical problem, and it tackles that problem by not invoking the stimulus response relationship, but by saying that any system evolves in such a way that the action, which is the integral L dt, L being the Lagrangian, that this action is an extremum. So it is a principle of variation which is at the foundation of Lagrangian mechanics, but then the consequences or the results of these two schemes are not different at all, and it is for this reason that the connections between symmetry and conservation laws can be seen in either scheme, because the physics is not different, the foundations are different, the platforms are different. The Newtonian mechanics rests on the cause effect relationship, on the principle of causality. The Lagrangian, the Hamiltonian schemes depend, they stem from the principle of variation, and these are the fundamental foundations. These are two different platforms, and both give you the trajectories, both tell you how a system evolves as a function of time. And the important thing to keep track of is this, that in solving any problem in physics, essentially what you are solving is this: how do you characterize the state of a system and how does the system change with time? If you answer this question, your problem is solved. Okay? So, you do it using either Newtonian mechanics or Lagrangian or Hamiltonian mechanics, and when you can't do it, when you come to terms with the fact that position and momentum cannot be known simultaneously and accurately, you need quantum mechanics, and then you say that the system is described by the state vector or the wave function, and how does this evolve with time? That is the Schrodinger equation. So, again the problem is the same, that the system is characterized by the wave function and its time derivative, its evolution with time, is what will solve the problem for you. Okay. So, both the variational methods and the cause effect principle of causality or determinism, they give you the solutions to the mechanical problem, but the platforms are different, the physics is the same, details are different. Of course, in this case you are able to deal with constraints and so on much more easier way. In Newtonian mechanics, if you keep track of every constraint, you can set up a detailed equation of motion taking into account every constraint, you will still get the same connections between symmetry and conservation laws, because that is where the physics is.
I heard that Mercury has some planet Mercury has some problem with these equations, which was later solved by Einstein
right.
in his theory of it. So, can you brief me about the problem with Mercury and these equations?
Well, it is a very interesting question, very its answer has very far reaching consequences in physics. Okay, now we have seen that if the force is strictly 1 over r square, okay, if that is what describes the force, right, then the orbit would be an ellipse and its major axis will be fixed. So, the orbit will not precess. Now, careful observations on Mercury tell us that Mercury orbit actually does precess. Okay. Now, what is the reason that it precesses? Now, there can be a variety of reasons. One is that the solar system is not just a 2 body system. Okay. Only if you solve just the 2 body Kepler problem, you will have ellipse as the solution, but then there are perturbations. There is not just the earth and the sun, but there is a Jupiter, there is a Saturn, there is a moon, right, and all of these will influence certain perturbations. But these perturbations are not the reason why the orbit of Mercury precesses. The orbit of Mercury precesses because Newton's law itself is an approximation. Newton's law presumes certain things. Okay. Newton's law is formulated in the domain of mechanics, which is essentially Galilean relativity, whereas the laws of mechanics are relativistic, and this was discovered by Einstein, and it is these relativistic consequences which are responsible for the precision of the orbit of Mercury. So, for this you have to get into the so called field equations which come from Einstein's theory of relativity, and those give you the correct orbit for Mercury. Now, it is rather remarkable that this was one of the first tests of Einstein's theory. So, it comes from the non-constancy of the Laplace-Runge-Lenz vector and so on, but the basic origin of that is the fact that the Newton's law of gravity is only approximate. It is a non-relativistic approximation to the correct law, which has to come from the theory of relativity. So, we will stop here for this unit.